Alright, it's day 11 on Advent of Code, and today's problem was a little bit of a doozy. It wasn't like super duper hard, but it was definitely, the problems have been escalating in difficulty, and this one had a few tricky parts to it. The premise of the question basically is some monkeys are throwing around our objects. We're worried about this, and so we have these worry values. But for each monkey, it has some operation to determine how our worried value. I'm just going to use this term worry value all over the place because it's important. And every time a monkey inspects one of our items, this operation tells us how our worry value changes. So in this case, we start with 79. When the monkey expects that, we multiply that value by 19. Then we have this test for each monkey. And this test determines whether the monkey will throw it to monkey 2 or monkey 3. So we see we have monkey 0, 1, 2, 3, and the basic, it's like 7 or 8 monkeys in the large input that I got. And so this test determines who gets this item next. So basically, we have 79. What happens? We'll multiply 79 by 19. In part 1, we'll actually then divide that value by 3, but that won't apply in part 2. Then we apply the divisibility test. And so if the result is divisible by 23, the monkey will throw this item to monkey number 2. If it is false, then monkey 0 will throw it to monkey 3 instead. So it's really a state evolution problem. We're just processing all these different events that are happening, but it's all still serial. So really it's just a matter of writing a good update function and looping through everything properly. What we eventually return, I think we need to keep track of how many times each monkey inspects an item, and then we take the two largest values of those and multiply them to get our final answer. So yeah, the two most active monkeys. And in the first part, we're running 20 rounds of this. So for one round of this, we'll process every monkey. So every monkey looks at its items, throws them to other monkeys, and then we move on. And once we've gone through every monkey, that's the end of a round. First part, we do 20 rounds. Second part, scale becomes a difficult problem. Scale in terms of the size of the worry values that we're dealing with, because we're doing 10,000 rounds, and in part 2, as I said, we're excluding that divide by 3 step. So we're going to get very, very large numbers if we're not careful about this, because if you multiply something by 19 and you do that 10,000 times, that's a big number, and we would prefer to keep numbers small. And the key insight for part 2 is that if you sort of take some number x and you take x times 19, well, the only thing we're keeping these worry values around for is to do these divisibility checks. So what we're actually going to keep track of is the modulus of our worry values compared to all of the divisibility checks. So, we need to know, after we multiply our number by 19, what's its modulus of 23? And it turns out you don't need to keep growing the number. You can actually just keep defining that in terms of the modulus, and the addition and multiplication operations will still work out. You'll still get the right results for your divisibility check. So, a little complicated to work your head around that, but that's, I think, the correct and intended approach for this. So let's move on to the code. So the parsing is a little bit tricky. Just there are a number of different elements of each of our different monkeys. So we have the starting items, we have the operation, and the operation can be one of 3 things. It can be multiplying by a constant, it can be adding a constant, it can also be squaring the old value. So we can take old times old. That's also a valid operation. But yeah, we just have all these different tests. Most of it is pretty simple. So like parse starting items, we get this string, we get parse positive number, we have to separate that by commas, and then we just return those numbers. Parsing the operation, we get, this is, again, the starting string. We can either have an add operation, a multiply operation. Each of these, all of the individual components are fairly simple, so you just have to have a good parsing library that can break all of that down and give you what you need. So we have this, we have this operation type, and that gets accomplished by these 3 parsers. We have the test part of this, which is returning how much we're divisible by, and then we have the throw statements where we determine which monkey we're getting thrown to. So each monkey has its own rule. So the rule has the operation, the rule has the divisibility test number, and it has the index of the monkey we throw to if the divisibility check is true or if it is false. So those are the fields of the monkey rule. Those don't change throughout the course of the problem. So what we're actually going to do, we're going to store all of the monkey rules in an array indexed by the monkey index. Yes, I think I said the right words there. But we also need to track the items that each monkey has in its. But we also need to track the items that each monkey has at the moment. So we need a hash map from the monkey index to a sequence of the values, the worry values for each of the items it has. Although, as we'll see in part 2, using an integer is not going to be enough here, but we'll get there when we get there. But really, we're done basically going through the input parsing code. So we just combine all of these different parsers together. We return the sequence of starting values. We return the rule, and we just combine those. Nothing too complicated is going on there after we get through all of the different steps. So how do we actually solve this problem? Well, this is really the first instance so far this year where I am using the state solution pattern, where basically we have a stateful type, and instead of having that update in a fold fashion where we're processing one new line of input, we're just processing a certain number of rounds. So in the case of the easy problem, we'll be processing 20 rounds, and so we have this recursive helper that just says, okay, play a round and then recurse with n-1 rounds remaining. That's all this function is doing. We're keeping our rules as a constant that just gets passed to all of our functions, and we just update the state type each time. So what does it look like to play around? Well, playing around is very simple. We just fold through the different monkey indices. So we have our array of rules. We just get the bounds. We get the range of that. That is our source of truth, so that we are looping through the monkeys in the correct order. So the round, we loop through the monkeys. Within each monkey, we loop through the items. So we have, okay, fold M, we have our item function. We'll get into that later. And we're just taking the first of our states, so the hash map from the index to the sequences, and we're just doing that for the corresponding monkey. We're looping through all of these items, or really these item sequences. Or we're looping through one sequence and going through the different items and processing each of them. At the end of this process, when we've gone through all of the items for a single monkey, we're just going to overwrite its sequence as empty. So we have seek.empty. We're inserting that into our hash map for this particular monkey. And what happens next? Now we need to actually process a single item for a single monkey. Now we're also storing an occurrence map in our state. What is this occurrence map for? This is tracking the number of times each monkey has inspected an item. So the very first thing we do in this function, we increment the key for that particular monkey. Easy enough. Then we get the rule for the monkey, because remember, we're passing our rules around as a constant, and we can just index that. And now we need to calculate the new worry value. So like I said, first we apply the operation, and then we divide it by 3 in the first part. Applying an operation, nothing's hard about that, at least part 1. We either just add, multiply, square it, easy. So we get the new worry value, and then we can perform the divisibility check. So we take worry 2, our new value, we mod that by our using the rule, the test divisible number. If that's equal to 0, then we use the true value from the rule, otherwise the false value. So this throw 2 is an index. This is the index of the monkey that will be receiving this item. So what do? Well, we look at all the items for the new monkey, so we get its sequence, and we append this item onto the back of that sequence. Put all the stuff back in our state, and we're done. So this is basically all the code we need for the easy part. Now, for the hard part, I could have come up with a better abstraction for this, but I ended up just copying a lot of this stuff, because the core of what needs to change is that instead of storing a sequence of integers, so up here we are storing monkey items, that's just to find that all the way back up here. So that's a hash map from integers, from a monkey index to just the sequence of integers. Down here, we're making this new type called modulo hash. And so we're storing a sequence of modulo hashes instead of integers. And how do we construct this? So we take our original items, and we also take the set of rules, because we need all of the divisible test values from the rules. So elements in rules, just source all of those, and then we insert for, let me remind myself how this is working. So for each divisible value, we map through those, and we return a tuple that is the divisibility value modulo, or, well, we take the x value and we take modulo on the divisibility check. And so remember, we have a sequence of these modulo hash values for each monkey. Instead of holding one worry value, it's holding this modulo hash in place of that. And the way we apply that, we can apply operations like this. So we take an operation, we take a modulo hash, and now we use map with key. We go through all of these different divisibility checks and we perform the correct operation, because the correct operation still works on the modulus. So we take the existing worry value, or the worry value replacement that is corresponding to each key, and we add our new value x, which, remember, that's coming from the rule, and then we modulo by the key once again. And we do this, we loop through all of the values in each modulo hash. So instead of applying an operation to a single integer, we're applying it to the whole modulo hash. And that comes into play when we have our play item hard function. So for part 2, we're saying, okay, we apply our operation, we don't divide by 3, but now how do we do the divisibility check in part 2? All we have to do is we take this value, and because remember, worry 1 is a modulo hash, so we can look at the divisibility number. If that divisibility number within this hash map is still equal to 0, then it is true. Then the total number, whatever that worry value is, however large it is divisible by that number. So we select true, and then the rest of the logic is basically the same. We still, add this worry value to another monkey's sequence. We still erase them for the monkey we have just processed. All this code, copied it, probably could find a good abstraction, but it works now for the hard part of this problem. And so what do we do now? We just have to, so for the first part, we solve the state with 20. Second part is 10,000. And in both cases, we get the occurrence map out. So we use second to pull that out of the stateful type. And then we need to do just a little bit of post-processing. We need to take all of the elements in that occurrence map. We need to sort them, reverse that to put the highest 2 at the front and take 2. And then multiply them. So a few different steps on that final list. What changes in the second part, they can be bigger numbers. So we need to use an integer. We need to return integer instead of an int here. But ultimately, that should work out. We put all these parts together, and we get our answers. And as you can see, I just ran my unit tests, and they all work, and we just get these very large numbers for the hard solution. So yeah, that is day 11. Definitely harder than most of the previous days. So stay tuned. Keep your eye on this channel. Subscribe to the Monday Morning Haskell channel and the email list so you can stay up to date with the new advent of code solutions as we go through them. We have 2 weeks left. And so we're not even halfway there yet, and the problems are already pretty challenging. So yeah, keep your eyes on this channel, and I will see you tomorrow.